Good evening. Okay, I feel a little bit sick. If I don't make sense today, let me know. Okay, good evening. Let's see, anyone has any questions? So we finished chapter 3 about integration techniques. So we're going to a totally different kinds of content now. So going to talking about sequences and series. Oops, what happened? Right, we're skipping the differential equations. So going to chapter 5, sequences and series. Sequence, infinite series, divergence, integral test, comparison test, alternating series, ratio. Right, we're going to cover all this. We're going to cover all 6 sections. Sorry, my head hurts. If I don't make sense, let me know, okay? The topics we skip won't be on the final. No, it won't. So it's not on the syllabus. So differential equations is not on the syllabus. It's scheduled for, it's been put in other course. So this textbook, right? So we're not going to cover that. All right, so sequences. So what do we want to do? We want to find the formula for a general term of a sequence. So let's see if we're given a sequence of numbers, right? Maybe we're able to find a general formula for that. Or calculate the limit of a sequence if it exists, right? So which means some sequence goes descending order. So, or some sequence may go ascending order, but it may be reach a certain number. Or no? Oh, you're right. Let me see what's going on. This one works, right? Okay. All right. So let me just go with this one. Okay, so the limit of a sequence. Then determine if the sequence converges or diverges. Right? Last time we talked a little bit about convergency and divergency. Convergency means it reaches a certain number. The number could be very big, but as long as it reaches a number, that means convergent. And divergence means it goes to infinity. It could be negative infinity or it could be positive infinity. So let's see some terms. So we use A1, A2, A3 to represent each term in the sequence. Right? A1 is the first time, A2 the second term, so on and so forth. So each number in the sequence is called a term. The symbol n is called the index variable for the sequence. So we could use set notation to represent, right? We use set notation, we say, okay, this is a set of ANs. N goes from 1 up to infinity. Or sometimes it's simply a set of ANs. So by default, n is a natural number. 1, 2, 3, 4, keeps going on. So let's see this sequence. So we have 2, 4, 8, 16, 34. And we observe there's a pattern, right? So A1 is 2, A2 is 4, A3 is 8, so on and so forth. So A1 is 2 to the first power, A2 is 2 to the second power, A3 2 to the third power, fourth power, so on and so forth. So that means this sequence can be written in a general form, which is a set of 2 raised by n. N goes from 1 to infinity. Or just a set of 2 n's. N represents a natural number. So we can describe this sequence in some other ways, since each term is twice the previous term. And we can also define this nth term of an in terms of previous term, an minus 1, right? So we use the previous one to determine the following one. So in particular, we define this sequence as a sequence of an's, where a1 equal to 2 for all n greater than or equal to 2, so the following terms. And each of the following terms, starting from the second term, can be defined as a recurrence relation. An equals to 2 times an minus 1, right? You see this one? First one is 2, double 2 get 4, double 4 we get 8, double 8 we get 16, double 16 we get 32, so on and so forth. So this is a preferable way. In this way, we related each one with the previous one and the current one, or the current one with the following one, right? So an plus 1 term will be 2 of an, so on and so forth. So let's see the definition. An infinite sequence, a set of an's, is an ordered list of numbers of the form. So this is the order, right? A1, A2 goes on. This n is called the index variable of the sequence. And each term, an, each number an is a term of the sequence. Some sequences are defined by explicit formulas. Sometimes we may have a formula for that, in which case an equals to a function of n. Okay, sometimes we're lucky, we can write each one as a function value. So nth term as f of n. You can think a1 as f of 1, a2 as f of 2, so on and so forth. If each term can be represented as a function in terms of its position, In other cases, the sequences are defined by using recurrence relation, just like this. The current term equals to something. The current term is defined by its previous term. So that's a recurrence relation. In a recurrence relation, one term or more of the sequence is given explicitly, and the subsequent terms are defined in terms of the earlier ones in the sequence. Right? The before 2, 4, 6, 2, 4, 8, 16, so on and so forth, we can see clearly, right? So first position to see this couple points. You see this, it has explicit formula 2 raised by n. Or as recurrence, we could represent it 2 times the previous term. So there are 2 types of sequences that occur often and given special names. So one is called arithmetic sequence, all right? Arithmetic sequence. And another one is called a geometric sequence. In an arithmetic sequence, the difference between every pair is constant, is the same. Let's see this one. We have 3, 7, 11, 15, 19. First, these numbers are in order, right? So what's the difference in between each two? So 3 to 7, that's 4, add 4. 7 to 11, that's add 4. 11 to 15, adds 4. 15 to 19, adds 4. So this is just the previous term being added 4 to it. So this is called an arithmetic sequence. Well, versus geometric sequence. Geometric sequence is we multiply, so 2 to negative 2/3, we could clearly see 2 multiplied by negative 1/3. Then negative 2/3 multiplied by negative 1/3, that's 2/9. Then multiplied by negative 1/3 again, that's negative 2/27. So that is a factor, right? It's a factor. So what is it? So the ratio between each pair is constant, doesn't change. Okay, so geometric sequence means the previous one, the current one is the first one multiplying by the same ratio. Okay, let's see this one. So let's come back to arithmetic. So we have 3, 7, 11, 15, 19. So we see A1 equals 3. And so AN, the current one, can be defined as the previous one add 4, right? Because each term just add 4 to the previous one. So we can use this to define. So this recurrence relation, we can use this one to define this sequence. And then we see this, okay, then we see the relation. So A2 equals 3 plus 4, A3 equals 3 plus 4, 4, A4 equals 3 plus 4, 4, 4. So we can write this one, A2 is 3 times 1 times 4. A3 equals 3 plus 2 times 4. A4 equals 3 plus 3 times 4. So in general, we can write this as a function. AN equals 3, right? A1, the first term, plus 4 times n minus 1, adding n minus 1/4. So A2 is adding 2 minus 1, 1/4. A3 is 3 plus 3 minus 1, which is 2 over 4, so on and so forth. So you see, now this can be represented by a function. Basically, AN equals to f of n. What's f of n? F of n is a linear function, right? It's a linear function. The rate of change is constant. So in general, arithmetic sequence can be represented as a linear function. So AN's term is just f of n equals to Cn plus b, a linear function, right? Mx plus b, so Cn. So geometric sequence, the ratio between two next pairs, so the two pairs next to each other, the ratio between them are the same. In this case, it's negative 1/3. So the first term is 2. The second term is negative 1/3 multiplied by the current one. It's negative 1/3 multiplied by the previous one, starting from the second term. And also we can keep writing that. So A2 equals to negative 1/3 multiplied by 2. A3 equals to negative 1/3 multiplied by negative 1/3, because each step, each from the current one to the next one, we just multiply by the same ratio, negative 1/3. So A3 is negative 1/3 square multiplied by 2. And then A4 is negative 1/3 cube multiplied by 2. Right? So on and so forth. So we can write in a general form. The nth term equals to 2 times negative 1/3 raised by n minus 1. So what kind of function? Exponential function, right? We can write an as f of n. F of n equals 2 times negative 1/3 n raised by n minus 1. Exponential function. So arithmetic sequence can be represented by linear function. Geometric sequence can be represented by exponential function. Okay, any questions? So you see this an equals to c raised by r, c times r raised by n. Right? We can think f of n equals to a certain number c multiplied by r raised by n, exponential function. Normally, we want to find, given us a bunch of numbers, we want to find a pattern. Right? So we want to find a nth term. So let's see this one. So A, we'll observe A1 equals to negative half, A2 equals to 2/3, A3 equals negative 3/4. Let's see, I'm going to just read this. First, note the sequence is alternating from negative to positive. Yes, right? Negative, positive, negative, positive. The odd terms in the sequence are negative. Even terms are positive. Indeed. So first term, third term, seventh term are negative. Therefore, the nth term includes a factor of -1 raised by n. Right? Because the first term just -1 raised by 1, so we get negative. Next, consider the sequence of numbers 1, 2, 3. The numerators are 1, 2, 3, and the sequence of denominators are 2, 3, 4, 5. So we can see that both of these sequences are arithmetic sequences. The nth term in the sequence of the numerator is n, and the nth term of the sequence of the denominator is just n plus 1. So we can represent by an equals to the nth term equals to -1 raised by n times n divided by n plus 1. What is this? A rational function, right? So nth term can be represented by a rational function, but this rational function has this alternating sign. So this is one thing. So we could think about it. So why, if arithmetic sequence can be represented by linear function, and geometric sequence can be represented by exponential function, so why do we even bother to make sequences? So this is one of the advantage why we want to make sequence, because with function representation, we won't be able to do this, right? So the nth term will be two functions. So in this sequence, it will be represented by two functions, one with a positive term, one with a negative term. So we could see, use a sequence, this is one of the advantages. We can do alternating sequence, so -1 raised by n. The sequence of numerators 3, 9, 27 is in geometric sequence, so that's B. Okay. So the first one, just alternating series with -1 raised by n divided by n plus 1. Well, let's observe the second one. So 3 over 4, 9 over 7, 27 over 10, 81 over 13. The sequences of numerators are 3, 9, 27, 81. We could see that's 3 raised by 1, 3 raised by 2, 3 raised by 3, so on and so forth. And the numerator of nth term is just 3 raised by n. So the denominator is 4, 7, 10, 13, 16. The difference is 4 to 7 add 3, 7 to 10 add 3, 10 to 13 add 3. So the denominator is an arithmetic sequence. So the first one is 4, so 4 plus 3, right? So 4 plus 3 times n minus 1, right? The first one, the second one is multiply 4 plus 1 of 3. The third one is 4 plus 2 of 3, so on and so forth. So we simplify that, so 4 plus 3n minus 1, that's just 3n plus 1. So the linear function. So nth term can be represented as 3 raised by n, the numerator. The numerator is geometric sequence or exponential function. and the denominator is a linear function, right? Or arithmetic sequence. So nth term is a rational function. It's not rational function, right? It's not rational function. So I'm gonna, make a lot of nonsense today. So my head really hurts. Anyway, so this is another advantage we can see why we're using sequence, right? Similarly for series later on, because the numerator, rational functions, the numerator has to be polynomial functions as well. But in this case, the numerator is exponential function. So we have this term, exponential function divides a polynomial function, right? So this nth term. So now we can see the advantage of using sequence instead of using functions. Any questions? Okay, let's keep moving. Okay, now you try. 5.1. So try to find the nth term for this sequence. This is an alternating series. Okay, I got it. But write your answer in the chat. The numerator is 1, so we don't have to do anything with the numerator. Just think about the denominator. And also it's alternating. Think about the alternating -1 raised by certain number. The first one is positive. So I'm taking attendance. 1 over -1 raised by n. Okay, Paul has answered. He's saying, Paul, I would like you to use -1, negative. So your -1 raised by n, the negative sign is outside 1, right? So Rajab is saying -1 raised by n plus 1 over, so the denominator, okay. Zachariah has denominator 2n plus 5. -1 raised by n. -1 raised by n, that's fine. That's right. Zachariah, check your denominator. You see the first n start with 1, right? So 2 times 1 will be 2. 2 plus 5 will be 7. Your first term will be 1 over 7. So how do you fix that? And Paul, you have -1 raised by n. If -1 raised by n, the first position should be negative. How do you fix that? Rajab, you have -1 raised by n plus 1. Put -1 inside parentheses, all right, to indicate -1, the whole -1 is being raised by n plus 1. I agree with Rajab's answer. Shahara, right. Look at Shahaya's, right, Shahaya's, good. Yes, it's over 2 n plus 3. Okay, pretty good, pretty good. What about the rest of you? Alexis is here, Alexander is here, Alejandro is here, Fujun is here, Darren is here, Jack here, James here, Kelly here, Nuzat, N-U-Z-H-A-T. You know, I worry about you. Where's your homework? Oh, try J's here. Good. I just replied your email. I know you're in the tennis team. You're playing for the school. That's great. Okay, but try to catch up with the class, all right? Because March 17th, so a couple of days later, you're going to have a first midterm. And every class is being recorded. So if you miss any course, try to watch the recordings. Okay, so anyone has question for this? Let's observe. So the first term is positive. So what do we do? So that means we need to do, there are a couple ways to do it, but I would put -1 around inside the parentheses, then raised by n plus 1, right? Because the first term is positive. That tells me the first term is -1 raised by an even number. So first one can be raised by 1 plus 1, right? 2. So -1 raised by n plus 1. But someone was thinking negative, then -1 raised by n. That's fine also. Well, that's exactly the same as -1 raised by n plus 1, right? It's a different writing, but it's, the neat writing is -1 with parentheses raised by n plus 1. Now, the numerator is constant. The numerator is 1, so we don't have to do anything with the numerator. Numerator will be 1 forever. We only have to think about the denominator. So A1 equals to 5. I mean, the denominator of A1 is 5. Denominator of A1 is 5, right? So that means the rest, so now then let's think about 7. So 7 equals to 5, the first term, the denominator of the first term, plus 2. Especially 2 times the position. What's the position of -1/7? Second position, 2, right? 2 minus 1. 9 is what? It's 5 plus 2 multiplied by 2, right? 9 is 5 plus 4. So 3 minus 1. So you see, then keeps going. So the nth denominator, the nth terms of denominator would be n. So denominator of an should be 5 plus 2 times n minus 1. Right? Then we simplify. We simplify as 5 plus 2n minus 2. We simplify again, we have 5 minus 2, so we get 2n plus 3. So that's why the nth term equals to -1 raised by n plus 1, right? -1 raised by n plus 1, then multiply by 1 over the denominator is 2n plus 3. Okay. So the -1 raised by n plus 1, then 1 over. Actually, I don't need to do the 1. I just have to do -1 raised by n plus 1 divided by 2n plus 3. Anyone has any questions? All right, let's keep moving. So I surely hope everyone participating. Okay, let's see this one. For each of the following recursive defined sequences, find an explicit formula for the sequence. So A is the first term is 2, the nth term is -3 multiplied by the previous one, right? So the current term equals to -3 multiplied by the previous one. So that means the ratio equals to -3. So this is a geometric sequence, right? Geometric sequence. So A1 equals to 2, A2 equals to -3 times A1 equals to -3 times 2, Then keeps going, a3 equals -3 times -3 times 2. The fourth term equals -3 raised by 3 times 2. So in general, an equals 2 times -3 raised by n minus 1, right? Exponential function, geometric sequence can be represented by exponential function. So in this case, it's 2 multiplied by -3 raised by n minus 1, right? So we can check the first term is 2. So 1 minus 1 is 0, -3 raised by 0, that's just 1, right? That's first term. Second term, 2 times -3 raised by 2 minus 1, which is 1. So that's 2 times -3. So in this case, you see the nth term. We're starting from the relation, recurrence relation, right? The current term is the -3 multiplied by the previous one. Now, we're able to write the current term as a function of the position, nth position, of its position. So the nth term is a function of its position. So A1, think about this as f of n. F of n, exponential function, right? So A1 just f of 1, A2 just f of 2, so on and so forth. Any questions? Okay, sometimes we want to change recurrence relation to a function. Sometimes we want to change a function as a recurrence relation. Okay, let's say B. The first term equals a half. The current term equals the previous term as half raised by n. Okay. So first term is half. Second term is the first term half plus half raised by n is 2. Is a half plus quarter, 3 quarters. A3, it keeps going, we add up, that's 7 over A. A4, so we get 15 over 16. Or let's observe the pattern. The numerator is a 3 to 4 to 15. Right? We can see 3, 7, 15. We observe 3 is 4 minus 1. 4 is perfect square, 2 square minus 1. 7 is A minus 1. A is 2 cubed minus 1. 15 is 16 minus 1. 16 is 2 to the 4th minus 1. So that's the pattern for numerator, right? So that's why numerator can be written as 2 raised by n minus 1. About the denominator, the first one is 2 raised by, is 4, right? 2 square. The second one is 2 raised by 3. The first one, the second one is 4, 2 square. The third one is 2 cubed. Then the fourth one, the denominator, I'm talking about denominator, right? 2 raised by 4. So this is 2 raised by position n, right? So the nth term can be represented as 2 raised by n minus 1 divided by 2n. We simplify this, 2n divided by 2n, that's 1. So 1 minus half raised by n. What is that? That's also an exponential function, right? Just with a little bit of transformation. Think about half raised by n exponential function. Negative half raised by n is a reflection, right? One of the transformations is a reflection. Reflection over x-axis. Then add 1 to it. That's a translation. That's upward shifted up. And also this is exponential decay, right? Because the base is a half raised by n, is exponential decay. Okay. And then we can see clearly as nth term goes on, we start with a half, 3 quarters, 7 over 8, 15 over 16. And this sequence will converge to 1 as n approaches to infinity, right? As n approaches infinity, 1 over 2 raised by half raised by n will approach to 0. So this, we'll talk about sequence converges later on. But this one Okay, this one's not good anyway. Oh, also this one is not exponential function, right? Exponential functions, we require the base to be positive. So we could see that's another advantage of talking about sequence. So with sequence, the base can be any, can be positive numbers, can be negative numbers. That's another advantage. So this one definitely not converge, right? We'll go to, especially it will jump around, you know, alternates with positive and negative values. All right, now you try 5.2. So the first term is -4, and the nth term is the previous term plus 6. So you know you will come up, it should come up with a linear function, right? Oh, my head hurts. Ah. Okay, while you do that, I'm going to check attendance. Oh, someone left already? Oh, Trey left. Trey J left. He has a tennis game. Okay, anyway. 6n minus 10. All right. Let's wait for more answers. All right. Anyone has any questions? Alejandra, Li Zhen, Alexander, Alexis. All right. So we just have a -4 plus n minus 1 multiplied by 6, right? And we simplify, we get 6n minus 6 minus 4, that's a minus 10. Yes. So 6n minus 10. James, what do you mean plus 6? Oh, okay. It's 6n minus 10. Yes. All right, good. Let's see. Okay, limit of a sequence. Why, with nth term, we can take a limit. Let's see this nth term. If you take a limit, right, when n approaches infinity, we get 1 for this. Let's see, A. Okay, so 1 plus 3n. So the nth term is defined as 3n plus 1. Well, that's linear function, right? As n approaches infinity, the function approaches infinity. For this term, for b, 1 minus half raised by n, as n approaches infinity, and the function approaches to, I mean the sequence, the nth term approaches to 1. C, if we have a negative, if we alternate -1, 1, -1, 1, right? The term alternates do not approach to anything as n approaches infinity, right? It just alternates, it jumps from 1, -1, -1, 1. So we can't tell. D, if we have -1 raised by n divided by n, we will have -1, so on and so forth. The term also alternates, but however, because the denominator becomes bigger and bigger and bigger and bigger, so the term also goes to 0. Even this is an alternating sequence. Okay, so some alternating sequence like C, it doesn't approach anything. But this alternating series, because the denominator gets bigger and bigger, So the whole thing approaches to 0 as n approaches infinity. Right? If we graph them, it's like this. You see this one, so the value keeps going, and this one, of course, it keeps increasing, but approaches to 1 for this one. Actually, this one, yeah, okay. And this one, it alternates. -1, 1, -1, it jumps around. But this one, we can see approaches to 0. So 1 minus half raised by n. So this one approaches to 0. Any questions? Just take a limit. So we can take a limit of a sequence, nth term of the sequence. So we see the behavior of the sequence. In two of the sequence, the terms approach a finite number, right? One approaches 0, another one approaches 1 as n approaches infinity. Other two sequences, the terms do not. So if the terms of a sequence approach the finite number as n goes to infinity, we see that the sequence converges, right? Or the sequence is a convergent sequence. Okay. Convergent exactly means this picture. So this picture tells the convergence story, right? As a number goes bigger, it just come to 0, approaches to 0. So we write it as a limit when n goes to infinity. The nth term is a finite number. So this finite number can be big or can be small, doesn't matter, as long as it's a finite number. If it doesn't, as the other two cases, right, either approaches infinity or negative infinity, or it just jumps around, we see the sequence diverges, or the sequence is a divergent sequence. Divergent sequence, right? Like this one. This one just jump, from 1, -1. This one gets bigger and bigger, bigger and bigger. Okay, let's see definition. A sequence converges to a real number L if for all epsilon greater than 0, there exists an integer n such that the distance between the nth term and the final number is less than epsilon for all n greater than or equal to n. So the number L is the limit of sequence, and we write the limit of an when n approaches infinity equals to L. Or just the nth term approaches to L. If you see this is somehow like a definition of continuous functions, right? Except for n greater than or equal to n. So what does this do? So this is one of the advantages, talking about sequence, versus talking about functions. If we talk about functions, as long as the numbers in the domain, we cannot ignore, right? But when we talk about sequence, we can ignore finite terms, which means if you give me a meaning terms, right? Up to a certain number, up to a certain term, if I can find a pattern for the rest of the terms, I can ignore the previous n terms. So this is the beauty of sequence. This is the beauty of a sequence also. I can ignore finite many terms. As long as the n-1 terms, I can find a formula for it. So in this case, we see the sequence is a convergent sequence. If a sequence does not converge, it diverges. And diverges means there's no such finite number. It doesn't approach to finite number. Okay, you can read all this. All right, this is more details about it. Especially if in the beginning, you feel like sequence, the idea of sequence is kind of confusing. Okay, theorem. Limit of sequence defined by a function. Consider sequence such that nth term can be represented by a function for all n greater than or equal to 1 if there exists a real number L. And also, we can, so you can make a list of, advantages of sequence or this, pros and cons of sequence, pros and cons of function. Function, we talk about domain, right? We talk about the domain to be an interval, which includes, natural number, whole number, rational number, irrational numbers. So function, we're working with, rational numbers and irrational numbers. And sometimes we can even work with complex numbers. So that's the beauty of function. But with sequence, we only work with natural numbers. All right, anyway, so if nth term can be represented for a function of n, but for n to be a natural number, if there exists a real number L such that when we take a limit that x approaches infinity, f of x equals L, then the nth term converges. Right? You see all those ideas come together. We talk about limit of function reaches a number, right? The limit exists. So that means the nth term converges. That means the sequence converges. So we can write as limit of the nth term n approaching infinity equals to a finite number. Okay, second theorem. Algebraic limit laws. Now this comes, if a limit exists, it's a real number, right? If a real number, anything we can do with a real number, so we can do with the limit of sequence. Limit of constant equals a constant. The limit, the nth term has a scalar, we can pull the scalar out of the limit. Limit of two sequence, the summation or subtraction of two sequence can be split into summation or subtraction of two limits. Limit of product of two sequence equals to product of two limits. Limits of the quotient of two sequence equals to the quotient of two limits, right? Because, any property for real numbers for limits provide the limit exists. Okay, if the limit does not exist, we cannot talk about this. And also provide, you talk about quotient, the limit of the bottom, the denominator one cannot be 0. Okay, you can go through the proof by the definition. Okay, I'm going to skip them. Okay, let's see these examples. We want to determine the convergence or divergence and find limits for this A, B, C, D. So the first one, 5 minus 3 over n squared. So definitely this, take a limit of this, that's 5, right? Because as n goes to infinity, 3 over n squared goes to 0. So the limit of first one is 5. Well, what about the limit of B? Oh, we see this is rational function. How do we find a rational function? It takes the leading term, so 3n raised by 4, negative 4 raised by 4n raised by 4. So the limit of B is a negative 3 over 4. What about C? Well, C is different, right? C, we have the numerator is exponential function, the denominator is a quadratic function. So what do? We can do mathematical analysis. So which function dominates? Which one dominates? So in this case, the exponential function dominates, right? So exponential function grows very fast, much faster than the quadratic one. So this one goes to infinity, so the limit does not exist. So that's divergent. And with this one, 1 plus 4 over n raised by n, we'll take a limit of this, right? We can put limit inside the raised by n's power. And of course, 4 over n, limit of 4 over n goes to 0. So there's a limit of 1. Limit of 1 is 1. 1 raised by n, still 1. So it's exactly same as when we, similar, except C. 1, 2, 3 is very similar as when we're dealing with functions. Right? The first one, well, we could think this way. We could use limit, split 1 over n, limit 1 over n, each one goes to 0, 0 times 0, 0. This one we can do this way. Right? It goes to 5. C, we could use this one. We can divide it by the leading terms. You get negative 3 over 4. And this one, this one we can use L'Hopital's rules, right? We could use L'Hopital's rules. L'Hopital's rule, derivative of 2 raised by x is 2 raised by x multiplied by ln2. Derivative of the denominator is 2x. Then take derivative again. So what does it mean take a derivative? Take a derivative means we want to find the change of rate, right? Change of rate. So we want to see, okay, who grows faster? So whose rate of change is dominates? So say in this case, of course, the exponential function dominates. It grows very fast. The rate of change is much bigger. So this one diverges because it goes to infinity. Any questions? Oh, D. Okay, let's see D. Let's go through D. So D, we can consider the function as f of x equals to 1 plus 4 over x raised by x. Oh, okay, how do we take the limit of this? So take a ln on both sides. Right, I don't think we talked about this strategy before. So, or maybe you have learned in other class. So when we take this kind of limits, so raised by x, then we have x in the denominator. So inside the parentheses, x in the denominator or numerator even. Then raised by x. So what do? We use a log strategy. So take a natural logs on both sides. Because why? Because we can pull out the x, the exponent of x up front, the log. So take the natural logs on both sides. So log of a limit equals limit of a log. So we can switch those two. So log of a limit equals the limit of a log. So when we take a log of this raised by x, we can pull x up front. So that equals the limit of times x ln of this. Then we can split that, right? So that's x. So L'Hopital's rules again. So we want to write, because we have product of two functions, we have x times ln of something. So we use L'Hopital's rules. We rewrite x as 1 over x put in the denominator. Then L'Hopital's rules give us, so what do we get? We get a 1 over, so this is a 1 plus, like, okay, so we get a 1 over 1 plus 4 over x, right, in the denominator. Then we have this 1 over negative 1 over x squared. Then we take a denominator of this one, take a derivative of this denominator. We also get a negative 1 over x squared. So that cancel each other, that can to be 1. So then when x approaches infinity, 4 over x approaches 0, so we get a 4. Okay, let's try to make sense of this. So this is to use log, take logs on both sides. Anyone has any questions? Let's go one more time. So D is D is this, 1 plus 4 over n raised by n. Actually, this is related to E. If you remember Euler number, Euler number is limit of n goes to infinity, 1 plus 1 over n raised by n. So this is somehow related with the E term. And when we have that, we take logs. We use log skills to do that. So we take logs on both sides. Because log of limit equals limit of log, so we can switch the two positions. Then when we take logs, the x in the exponent, we can pull to the front of log. So we get x multiplied by ln of this. Then we use L'Hopital's rule, because when x approaches infinity, we have infinity multiplied by 0. Or what's infinity multiplied by 0? It's an indeterminate. So what do? We use L'Hopital's rules. Okay, any questions? Oh, okay, right here. That's e raised by 4. So 1 plus 4 over x raised by x. When x goes to infinity, that's Euler number raised by 4. So whenever we have this kind of limit terms, we take a logarithm to deal with it. Okay, any questions? Would we have to prove the answer the long way as in this example, or how you deduce it quickly? Well, this is the only way. For this one, if that's the question ever, so C, right, I mean D, for D, right, that's the only way to do it, to deal with it. Because you see, we have an n in the denominator, we have an n inside the parentheses in the denominator. We also have the n variable as exponent, right? Think about, in the functions we have learned, what kind of function is this? We have never dealt with a function like this. This is not defined by the basic functions we know. Right? 4 over n is rational. Then raised by n is exponential, but we do not have combination of rational and exponential functions. So that's one of the beauty of dealing with the sequence. So what do? We have to use log. We have to use log. So let's go back again. Let's go back again. So we rewrite as this: y equals the limit, doesn't matter x or n, n approaches to infinity, 1 plus 4 over n raised by n, right? You read by x, that's okay. So we take logs on both sides. So we get ln y equals to ln of this limit. The beautiful thing is, take logs of limit, it's same as limit of the log. If you want to see proof, you can find it. So we can switch those two signs. So log of limit, we can switch limit to the outside, that equals the limit of a log. And with log, we can pull this exponents of x up front of ln. Then we use L'Hopital's rules. So we use L'Hopital's rules, we get ln y equals to 4, right? So ln y equals to 4. Then that means y equals to e raised by 4, because ln is base e. ln y equals to 4. So y equals to e raised by 4. So that means D approaches, so D converges. D is exactly the definition, actually, limit. When we take a limit, that's the definition of e raised by 4. So e raised by 1, so e is the definition of limit of 1 plus 1 over n raised by n. That's the definition of e. And prove that is also proof limit of 1 plus 1 over n raised by n equals e is the same way, exact same way. Exact same way as this. Take logs on both sides. Then in the end, we get 1. In the end, we get a 1. So that's why limit of n approaches to infinity, 1 plus 4, 1 over n raised by n equals to Euler number. Euler number. That's the definition of Euler number, and also that's the proof of Euler number. Any questions? You could practice. You could change this 4 to be any other number. Okay. Change this 4 to be 5. The answer should be e to the 5. Change this 4 to be 10. You know, the sequence should be e to the 10, so on and so forth. Okay, try 5.3. So that's a sequence, 5n squared plus 1 over e to the nth power. All right. So determine whether or not the sequence converges. By analysis, right? By analysis, and e to the nth power grows much, much faster than quadratic function, 5n squared plus 1. So that means this sequence should go to 0 at a certain point, approaching 0. So, but you can try it, you try it. That's right, this would converge to 0 because the denominator dominates. You could think as, yeah. Okay, anyway, so let's skip this. So quadratic function, exponential over exponential function dominates. But when we prove it, we have to go through this. It's similar as C, right? When we prove, we have to go through this. We have to use the L'Hopital's rules. Because both goes to infinity, we have to use L'Hopital's rules. Okay, third theorem. Continuous functions defined on convergent sequences. So consider a sequence and suppose there is a real number L such that the sequence converges to it. Suppose f is a continuous function at the number. Then there exists an integer n such that f is defined at all values of the terms in the sequence for all n greater than or equal to n. And the sequence f of a nth term, f of nth term converges to f of L. So that goes along with the definition of continuous functions. Okay, that's not such a big deal for us. Let's see this one. Limits involving continuous functions defined on convergent sequence. Let's see this one. So determine whether the sequence cosine 3 divided by n squared converges. If it converges, find its limits. Since the sequence is 3 over n squared converges to 0, and the cosine x is continuous at 0, so we can conclude that the sequence cosine 3 raised by n squared converges to cosine 0, which is 1. So this is just using the theorem, right? Using this theorem. Okay, squeeze theorem for sequence. So this is important. So let's see, we have 3 sequences. So A, B, C. Suppose there is an integer capital N such that those 3 are in order. So sequence A less than B, less than B, less than C for all n greater than equal to this n. So what does this mean? This means, you know, think about we have 3 sequences, all right? 3 sequences. And it may not be every term in this order. we can ignore finite many terms. So this n greater than or equal to n means that. Means we can ignore finite many terms. Okay, we can truncate. We can truncate each sequence as long as the following sequence we can put in this order. So this just mean that we can forget about the finite many terms that do not in this order. If there exists a real number L such that the limit of sequence A equals to the limit of the sequence C, the fourth is the middle one, right? So the squeeze, think of the squeeze, okay? A sequence on the left-hand side, C sequence on the right-hand side. If those two, converges to the same number, so the fourth is the middle one. It squeeze the middle one to converge to the same number. So, right, so this squeeze theorem is quite important. I think remember when we learn limits, right? We also use squeeze theorem. Sometimes it's difficult to find the limits for certain things, for certain function, but maybe we can find the two easy functions, right? We use the two sides to squeeze the middle one, the limit of the middle one. So the same idea. So let's see those two examples. So the first one is cosine n divided by n squared. The second one is negative half raised by n. So cosine is bounded by -1 and 1, right? So then divided by n squared, we can just divide by n squared. So that means -1 over n squared. So cosine n over n squared is bounded by -1 over n squared and +1 over n squared. And then when we take a limit of this, we take a limit of these three things. The limit of the left-hand side, -1 over n squared goes to 0. The limit of the right-hand side, 1 over n squared goes to 0. The fourth is the middle one, cosine n over n squared goes to 0. Okay. This is very useful, right? For this one, for B, we think about, so we have negative half raised by n. So that's bounded in between of -1 over 2n and +1 over 2n, right? So lower bounds, upper bounds, as long as we can find the lower bound and upper bound. We'll take a limit of that. So limit of right and the limit of the left all goes to 0. The fourth is the middle one. Even it's alternating series, fourth is also goes to 0. Any questions? All right. Okay, so you try this one, 5.5. I'm going to check your attendance. Let's see. Okay. Okay. Ali is here. Pause here. Damani is not here. Woodley is here. Jack's here. Beach is here. Zacharias. Okay. Jameson. Pimple. Oh, a Chemical is not here today. Okay. All right, let's see. So 2, right? Yes. So it's very similar to the previous one. Because we have 2n divided n, which is 2. So limit of 2 is 2. Then negative sine n over n, we can use the same method. Squeeze, right? 1 over n. We can squeeze negative sine n over n in between of negative 1 over n to positive 1 over n. Well, limit of negative 1 over n goes to 0. Limit of 1 over n goes to 0 as n approaches infinity. So that's why it's 2. Okay, good job. Bounded sequence. So that means, so a sequence is bounded above if every term is less than or equal to m. So we have an upper bound. So the sequence has an upper bound. A sequence is bounded below if it has a lower bound, right? All the sequences are greater than or equal to a certain number. A sequence is a bounded sequence if it's bounded above and bounded below. So we have, so a sequence is bounded in between of two numbers. If a sequence is not bounded, it says unbounded sequence. So convergent sequences are bounded, of course, right? If a sequence converges, then it's bounded. Let's see some definition. A sequence is increasing for all n greater than or equal to n naught if the previous one, the current one, is less than or equal to the next one, the following one, right? We can imagine it increases. So what does n greater than or equal to n naught mean? That also means, you know, we can ignore the previous, you know, we put the sequence in order. Okay, sequence is always in order, all right? Sequence is always in order. So we put sequence in order, except alternating sequence. If it's an alternating sequence, the negative ones in order, the positive ones are in order. So for this one, it's the same n greater than or equal to n naught, also means same as before, you know, n greater than or equal to a certain capital letter N, means we can ignore the previous terms. So decreasing if the current one is bigger than the following one, right? Of course, it decreases. Monotone sequence. So sequence is a monotone sequence if it's increasing for all or decreasing for all. Right? A sequence is a monotone sequence for all n greater than some, you know, from certain point, from certain term. Okay, let's see this. Monotone convergence theorem. If a sequence is a bounded sequence, remember bounded sequence, it means it has a lower bound, it has an upper bound. And there exists a positive integer, a naught, such that the sequence is monotone for all, ignore certain terms. Then the sequence converges. So let's see using the monotone convergence theorem. So A is a sequence with 4 raised by n for numerator, denominator is n factorial. N factorial. So we could write some terms, right, to become intuitive. First term will be 4, second term will be 8, then third term 32 over 3, fourth term is also 32 over 3, fourth term, oh yes, because 4 divided by 4 is 1. So on and so forth. So at first the terms increases, right? So 4a and 32 over 3, that's almost 11. So 4 to 8 increases. Then 32 over 3 is almost 11. So 4a 11 increases. Right? Then 128 divided by 15, that's less than 10. So that's less than 11. So it becomes, so except those 4 terms, the first 3 terms, it becomes decreasing. So at first the term increases. However, after the term, the term decreases. So this is a monotone sequence. In fact, the terms decrease for all n greater than or equal to 3. So ignore the first 3 terms, it becomes a decreasing sequence. So we can show this as n plus 1 term equals to 4 raised by n plus 1 divided by n plus 1 factorial. And this one can be written as 4 over n plus 1 times 4 raised by n over n factorial, or 4 raised by n divided by n factorial, that's the nth term, right, times nth term. And we could see this is less than or equal to a nth term, right? Because as long as n becomes bigger than or equal to 3, this is 1. This is 1, and smaller than 1. So this number, it will be less than or equal to 1. So it's a decreasing sequence. Then we could use the monotone convergence theorem. So we'll take limit of n plus 1 term. It's same as this. And of course, this one goes to 0, right? When n approaches infinity, 4 over n plus 1 rational goes to 0. Right, so this is using the theorem. So B is the nth term defined recursively as this. The first term is 2, n plus 1 times the an divided by 2 plus 1 over 2an. So the first part is linear, so half of an. The second part is rational. So what do we do? We got a couple of terms. We have 2, 5 over 4, 41 over 40, so on and so forth. So that sequence is decreasing and bounded below by 1. 2, 5 over 4, 41 over 40. Okay, to show that the sequence is bounded below by 1, we can show this one is always greater than or equal to 1. To show that, we can write this way. We can combine those 2 terms. Then we see this always greater than or equal to 1 when n positive, if and only if, of course, right? So we multiply 2an on both sides. An squared plus 1 greater than or equal to 2an. All right. This just becomes quadratic inequalities, right? To solve the quadratic inequalities, so we get a perfect square. So an squared minus 2an plus 1, that's just an minus 1 squared greater than or equal to 0, which is always true, right? Because it's a perfect square. Perfect square cannot be negative. So take limit of that. Limit of the first part. So limit of an over 2. So let L be the limit of an. Right, so that would be L over 2 plus 1 over 2L. Right? So L equals L over 2 plus 1 over 2L. Then we can solve this. This also becomes quadratic equation. So we get 2L squared minus L squared minus 1. Then we can factor this. Okay? Oh, no. That's another L squared. So 2L squared minus L squared is L squared. So we'll get L squared equals 1. So L equals plus minus 1. Since all terms are positive, the limit cannot be negative. So the limit will just take the positive value. The limit equals to 1. All right, so that's this one. So this is use monotone theorem. Okay, Fibonacci series or Fibonacci numbers, the rabbit story, right? It's one starts with 1, 1, 1, 3. Let me see if it lists any numbers. No. So the Fibonacci sequence is defined as this. So the nth term equals to the addition of previous two terms. Right. So I think it's 1, 1, 2, 3, 5, 2, 3, 5, 8, 13, so on and so forth. All right, so it starts with 1, 1. Fibonacci. Should I write? So 1, 1, 2, 3, 5. Just keep adding the two terms. So 5 plus 3, that's 8. 8 plus 5, 13. 13 plus 8, 21. 21 plus 13, 34. So on and so forth. Okay, keeps going. Just keep adding two terms. So this is something about the Fibonacci sequence. There's something golden ratio. So the ratio in between of two terms, so the current term with the previous term, so the ratio is something called a golden ratio. This is 1 plus square root of 5 over 2. And the people find out in the nature, in the nature, golden ratio is being applied for human body, for plants, for flowers, basically everywhere, for construction. Okay, so that's it for today. So the sequence, all right? So we see why we need to use a sequence. Because some problems function cannot, we cannot model with functions. So basically functions are limited to model some the real world. So what do? We can model with a sequence. And next class we're talking about series. And we will see converging series. It's just functions also, continuous functions. So there are relations, the overlapping areas of sequence with functions and series with functions. But we do see the advantage of, making the math constructor of sequence. All right, I think I'm gonna finish class earlier today. I'm so tired, my head hurts me. And anyone has any questions? Okay, thank you, Paul. If no one has any questions, I'm going to finish here, all right? And I see you next Tuesday. I'm going to assign you homework. Okay, I just need some rest. My head hurts. All right, thank you, guys. Okay, have a good night.